Hello there. Welcome to the Learning of Engineering tutorial video lecture. In this video lecture, we are talking about columns and struts. We know these columns are widely used for the carrying the axial loads when the member is in the vertical direction. When the member is not going to be vertical direction, that is the main purpose of these columns are going to be to carry the either tensile loads or maybe the compressive loads. And because of this, struts are widely using for the movable objects. That member, axis of that member may not be in the vertical directions, that may be also inclined direction. For the best example of the column is the pillar in a house, or the building is consist of number of pillars. In this case, what is the condition we do have? The both ends are going to be fixed. Suppose this is going to be the column and both ends are going to be the fixed, and the load is coming from the top. And due to these reasons, what will happen? This member is going to be start to buckling, and we must be designed to overcome these kind of the phenomena existed in the column. So here the today topic is the crippling load, because this crippling load is helping to bend the objects. That means it's trying to deflecting from the mean position of the object. The crippling load when both ends of the column are fixed. So to illustrate this statement, I had given here. So can you see the dotted lines I mentioned? One end is going to be fixed, another end also going to be fixed. That ends I am going to be calling A as well as the B. A, B is going to be the B, that is the column is going to be fixed. At the same time, it consists of over a length L, and it has a uniform cross section. That's maybe a circular cross section, or maybe a rectangle, or that's going to be a square cross section. That depends on the requirement that engineers are going to be decide which kind of cross sections we have to use for the specific buildings. And this is going to be the cross section is there. At the same time, the load is going to be acting at the top of, that means at point B, because it is in the vertical direction, and that load, whatever the load is coming, that's going to be calling your buckling load or going to be the crippling load. The reason behind is that it is trying to buckle the objects in the transverse to the axis of the member. So there we can see, and due to this P, the member is going to be started to deflecting in this direction, because both ends are going to be the fixed. And we are assuming that the deflection going to be like this concave shape. So then what is happened in this case? At the same time, when the object is trying to move in this direction, there is going to be a fixed end moments are going to be generating to resist that kind of the deflection at the fixed ends. That I represented here. The fixed end moments is going to be the M naught here at A as well as the B. So can you see here, they are going to be acting in the both are in opposite directions. Right? So that's going to be, this is acting in the clockwise, suppose it's anti-clockwise, that is the clockwise. That depends on the deflection of the material, and these moments are going to be starting. So now what I'm going to do, I want to develop, and what is the crippling load? What is the maximum crippling load this material can handle? So that mathematical model helps to understand such kind of the behavior of the system. So now what I'm going to do, I'm going to be considering one point, some point on the deflection of the beam that's going to be, that is existed at y distance from the axis of the member, right? That is in the transverse directions we calculated, that is the deflection of the member. And similarly, from this horizontal, this is going to be x distance it is existed, alright? So that's going to be the point I have considered here. Suppose you can consider the point C. The point C, it is existed on the deflection of the member from the y axis, that is the axis of the member is going to be the y distance. From the point, that is the end A, it is going to be the x distance it is there. So now we need to find out the bending moments. As we know, because of these bending moments already it is going to be acted. So then what will happen in this case, because of this deflection also, because of this load, the deflection is going to be coming. So that points we are going to be mentioned here. That's going to be M naught is going to be the fixed end moments are there, and because of this load, it is, can you see the axis of these members are going to be changing. That's going to be the P into Y we are getting. So now we will take the summation of these moments at one point. So now we can see the moment at these sections we are going to be considering, that's going to be M naught minus Py we are going to be getting, right? So once it is there, as for the deflection of the beams, we are going to be taking moments at the section also, that's going to be MC is equal to EI into d square y by dx square we are getting. So now what I am going to do, these two equations I am going to be equating. So then what is the equations we are going to be getting here? So that's going to be summation of the moments if I am going to be taking. So this is going to be MC is equal to, this section's at naught is going to be m naught minus py we are getting. So this is going to be ei d square y by dx square m naught minus py. So from this equation we are trying to simplifying further. So how we are going to be simplifying that equation? So that I am going to be taking here, that's going to be d square y by dx square is equal to m naught by ei minus p by ei into y we are getting. So once we got it, and then ei I have substituted in this direction. So now that simplifying equation is equal to d square y by dx square plus p by ei into y is equal to m naught by ei, we got it. And further simplification I am going to be doing here, I am multiplying and divided with the crippling load. So that's going to be m naught by ei into p by p. So from this equation I am writing d square y by dx square p by ei into y, that is equal to p by ei m naught by p, we got it, right? So from this equation I am going to be trying to do the integration, and that I am going to be getting the differential solution I am going to be getting. So here I have written the solution for the differential equation for this. So that we got it, y is equal to c1 cos and x into square root of p by e, and similarly plus c2 sin x p by e under square root plus m naught by p. Now in this case the two terminologies are going to be the constants, that's going to be the c1 and the c2, these parameters we need to be calculated. Then how could you calculate these two parameters? That we are going to be considering by the boundary condition. Suppose the boundary conditions I am taking over here, the first one we are going to be taking at a. So the boundary conditions at a is equal to, then what is the value of the x? In this case, what are the parameters we do have? X is the variable, y is the variable are going to be. So then at a is equal to, what is the x? The length of the column x is equal to 0, and y is equal to, y is nothing but the deflection of the system, that is also at a is equal to 0, and then slope also existed, dy by dx is equal to 0. This is the first boundary condition. Now I am going to be taking the second boundary condition here. The second boundary condition I am going to be taking at b. So now you can tell me what is the value of the x. We know that the length is going to be the L we have, that's deflection at the b is equal to 0, and the slope also that is existed, that's dy by dx is equal to 0. And by using these two boundary condition I am trying to find out here. I am going to be taking the first boundary condition, I am going to be substituting in this equation 2. Right? So then if I am going to be substituting boundary conditions, y is equal to 0, x is equal to 0, right? So then if I am going to be substituting, what I am getting? So that y is becomes 0, c1 cos x is there, x is going to be 0, the square root of p by ei, plus c2 sin x is going to be 0, square root of p by ei, plus m naught by p, we got it. So we know the 0 into this parameter will become 0, here also 0 we are getting. So then sin 0 is equal to 0, then cos 0 is equal to 1. So that I am going to be taking over here, so that's going to be 0 into c1 plus m naught by p, we got it. From this equation the c1 is equal to minus m naught by p, I got it. By substituting the c1, right? That means by substituting the boundary condition, the x as well as the y, we got this equation. So now if I am going to be substituting in that equation, we need to find out the C2 parameter also. Before that, we are going to do some simplifications over here. So we have substituted x is equal to 0, y is equal to 0. And there is another parameter dy by dx, that is going to be the slope also there. So that I am going to be, in order to substitute that one, I am going to be differentiating with respect to, so I am going to be differentiating with respect to the x. So differentiate with respect to x. So dy by dx, and this is going to be c1 is the constant, the cos integration, sorry, the cost differentiation, we are getting the minus. That I am going to be keeping here is the minus sine x square root of p by ei. Then this derivation will become here the square root of p by ei, we got it, right? So plus C2 sine derivation will become cos parameter, that's going to be the cos x into the square root of p by ei, we got it, into this parameter differentiation, that's going to be p by ei, I got it. So can you see here, once I am going to be getting this equation, I am going to be substituting. Here is going to be, what are the variables here? Dy by dx as well as the x, these two parameter. That's going to be x is equal to 0, dy by dx is equal to 0. Alright, so when I am going to be substituting in this equation, so then what I am going to be getting, this parameter will become 0 and this is going to be sine 0, so that's going to be minus c1 sine 0 p by ei, right, the square root of p by ei, we got it, plus c2 cos 0, so here cos x will become 0, square root of p by ei into square root of p by ei, we got it. So further simplification, it will become, the sine 0 will become 0. So then what I am going to be getting here, this is going to be the 0 is equal to, cos 0 is equal to 1. So that is equal to C2 into square root of p by ei I am getting. So there we can see either C2 will going to be 0 or p, as for this definition, the C2 is equal to 0 or the square root of p by ei is equal to 0. So there we can see C2 is 0 and this one. So it is not possible. That means the P load is going to be, a buckling load is going to be existed on this one. So that means the C2 will going to be 0 over here and the P by ei under square root is not never going to be equal to 0. Alright. So from these assumptions, C1 and the C2 values we are going to be substituting in our original equation. After getting the C1 and C2, then I am going to be substituting in this equation. So in this first equation, if I am going to be substituting, so that what I am going to be getting. So here the y is equal to, C1 is equal to minus m naught by p cos x into square root of p by ei plus C2 is equal to 0. That means this parameter will going to be 0, m naught by p we are getting. So once we got this equation, I am going to be simplifying. I am going to be considering, this is going to be the equation 3 I am going to be considering. So now we got this third equation. I am going to be substituting the boundary conditions too. So what is that one boundary conditions too? BC2 is equal to, here x is equal to 0, sorry, x is equal to the L, comma y is equal to 0, dy by dx is equal to 0. These are the boundary conditions of the secondary boundary conditions. Then I am going to be substituting here. Can you see, if y is equal to the deflection at b is equal to 0, that is equal to minus m naught by p cos x will become L square root of p by ei, right, plus m naught by p. So there we can see further simplifications we are trying to do. I am going to be taking these terminologies to the left side. So that I am going to be taking m naught by p is equal to cos L into the square root of p by ei, I got it, into m naught by p. So this will going to be vanish according to mathematically. Then this parameter is going to be cos L into p by ei square root, that is equal to 0, we got it, or that is equal to, sorry, 1 we are getting. So then when the when this parameter is going to be 1, when cos 0 is equal to 0 or cos 2 pi is equal to 0. So for this case I am going to be considering cos 0 or cos 2 pi or cos 4 pi time like this. So then what happened, this parameter will going to be 1. So that I am going to be writing the least parameter I am going to be considering here. What is the least parameter? We should not keep the 0 here. We are going to be taking the least parameter here is going to be the 2 pi. So that I am going to be taking here the cos L P by EI, the square root, that is equal to the cos 2 pi. If I am going to be simplifying this equation, I am going to be getting here L P by E under square root is equal to 2 pi. So then further simplification of this one, P by EI, right? So that is equal to 2 pi by L whole square we are getting. Can you see? Then finally we need to find out the value of the P. So when I am going to be taking the value of the P is equal to, this will become 4 pi square EI by L square we are getting. Right? So from this one, the crippling load P is equal to 4 pi square EI by L square we got it. So that means the load, how much load we can act on this one? That's going to be 4 pi square EI by L square we got it. So this is the way we are going to be calculating the crippling load or the bucking load is acting on that system. First we have taken that the differential solution equation. So the differential solution equation I have taken, then after I substituted the boundary conditions 1 as well as the 2, then I got it the reduced equation. Then once it is going to be reduced, then I have used the boundary conditions 2, right? And after that we got the magnitude of the P. So I hope you are able to understand the way we derived the mathematical model for the understanding or the identifying the response of a column when the crippling load is going to be acting. Still, if you feel any confusion, please put in the comment section so that I can reach you out. Thank you.